Dr. Godez.
Hey Tyler.
We're back for another post-class video.
Back for another post-class video, and this one is on electrolysis.
Oh.
Yeah, so we learned in class about how current relates to moles of a substance.
Okay.
Right, and Faraday's constant is going to tie that together. And so I'm just going to do another example. Right, so the example is, again, it's tying in something extra, not just using the current relationship, but
right,
tying it into some chemistry. So what volume of gas is produced by electrolyzing water for 7.5 hours and a current of 5.66 amps using platinum electrodes?
Wow.
Ooh, okay, so we're going to electrolyze water, it's going to make a gas, we're using platinum electrodes, da-da-da-da. So, where do we start?
We should start with the reaction.
With the balanced reaction, right? Electrolyzing water. Well, what does that mean? That means putting electricity in water to make it split apart into its component parts. And we did this reaction in class, and so I'll just write it out. And so this is our reaction. I have a suspicion, and I better put my states of matter because we're talking about a gas. So maybe that's important. Right, so this reaction produces 3 molecules of gas, or 3 moles of gas on a molar basis.
Right, per 2 moles of water.
Per 2 moles of water. Since I'm doing electrons, I'm passing current, I'm pretty sure I'm going to need to figure out how many electrons are transferred in this. And again, in the activity, what we did was split this up into half fractions and looked at how many electrons were in each half fraction. But I want to show you a different way to do it without half fractions. And this is by using the oxidation numbers. Right? So you can figure out number of electrons transferred by looking at oxidation numbers instead of splitting it up into half fractions. So the first step is to assign oxidation numbers to everything. Hydrogen, it's +1 when it's with anything, non-metals. Oxygen, -2. Elements are 0. Okay? So we can see that the hydrogen goes from +1 to 0. Well, when it changes by 1 oxidation number, that's 1 electron, right?
Right, and it's getting reduced.
And it's getting reduced. How many hydrogens are there?
2, 4.
4 hydrogen atoms, 2 hydrogen molecules, right? But 4 hydrogen atoms, and oxidation numbers go with the atoms, so 4 atoms, each gets 1 electron, that's 4 electrons.
Got it.
So 4 times 1. How about for the oxygen? We can do it for the oxygen too. Oxygen's -2, it goes to 0. So each oxygen atom loses 2 electrons. Yeah. So it loses 2 electrons, but again, there are 2 oxygen atoms, and so 2 times 2 electrons is 4. So 4 electrons gained by the hydrogen, 4 electrons lost by the oxygen.
Now we know N.
N is not 8, right? These are the same 4 electrons, they're just moving from one place to the other.
Right, so before.
N equals 4. So that's kind of preliminary. That's a lot of work before I've even written out an equation, right?
Yeah.
Before I've even used the numbers in there. Okay, well, current and time. And so I'm going to use that equation that the charge transferred, C, equals the current times the amperage. Oops. Current times time. Current's units are amperage.
Right.
Okay? And so I just plug these numbers in. Charge equals 5.66 amps. And what is an amp?
An amp is a coulomb per second.
A coulomb per second. So coulomb per second. The time is 7.5 hours.
But we're going to want to convert that so we can cancel the seconds.
Yeah, we want the time to be in the same units. So how do I get rid of that?
Multiply it by 60 twice.
Yep. 60 seconds per minute, minutes are going to cancel. Okay, that gives me 1.53 times 10 to the 5th coulombs.
Right.
Okay, so I have my charge straight from those numbers, and now I got to tie it back into the chemistry. And what allows you to tie charge back to chemistry, i.e. moles and masses and all that kind of stuff,
Right.
is that Faraday's constant. Faraday's constant, 96,485 coulombs per mole of electrons.
Okay.
So how am I going to use that with this number?
Well, if you just think about units, you want to cancel your coulombs,
Yep.
right? So you would divide it by Faraday's constant.
Exactly, divided by Faraday's constant. So I'm going to multiply by 1 mole electrons per 96485 coulombs.
Right. And what he did was just take Faraday's constant and flip it.
Yep. Yep. And what do I get? 1.58 moles of electrons.
Right.
Okay. Now comes the tricky part.
Right, because now how we're going to relate moles of electrons back to this that we have here.
Yeah, I'm asking about volume of a gas. I'm asking about volume of these gases that are produced. I have moles of electrons, and I know that if I have moles of a gas, I can use the ideal gas law to calculate a volume.
Right.
Right? So I have to use the balanced equation to figure out what's the ratio of moles of electrons to moles of gas.
Right. And in this reaction, we know that 4 electrons get moved for 1 mole of this gas and 2 moles of hydrogen gas.
Exactly. So that means that my ratio is going to be 4 electrons, because that's how many are transferred in the reaction, and it produces 3 gas molecules. 3 gas.
Yeah.
Okay? The electrons are going to cancel, and I'm going to get moles of gas. And when I do that, I end up with 1.187 moles of the gas. Now you could have done it separately. You could have figured out how many moles of the hydrogen by using 4 to 2, and then how many moles of oxygen, 4 to 1, and then added them together to get the total moles.
Right.
Right? Because this is a mixture. It's a mixture of both gases.
Right. But we know that by ideal gas law, it doesn't really matter what gas it is.
Exactly, because they're ideal.
Right. They are ideal. Isn't that great?
They don't interact. So, then the last step is just inserting this into the ideal gas law, right? PV equals nRT.
Right. And we know N.
Well, so here's where it gets tricky, right? We don't have enough variables in chemistry, and so we use the same variables for a whole bunch of stuff.
Right.
Right? So I've written up here n equals 4, but guess what? That's not that n. This is the number of electrons transferred in the reaction. What does n stand for in the ideal gas law?
That is the number of moles of gas.
Number of moles of gas.
And that's what we calculated down here.
Exactly. The other tricky thing is this R value. For the last few weeks, we've been using a value of R that's the energy units.
Right, to give us joules. Or
To give us kilojoules or
use
joules.
Right.
Yeah, 0.008314.
Mhm.
But in the ideal gas law, we have to use the units of volume and pressure and things like that, which
Right.
is 0.08206 liter atmosphere per mole K.
Right, because those are the units that we're working with now.
Right. Okay, and so I can rearrange this, volume equals nRT over P. Okay, and so I'm going to assume that you're all hands at the ideal gas law and can figure out that this gets converted to 29 liters of gas, about
Right.
29 liters of gas. Okay, so what are the lessons that we learned here?
The lessons that we learned are always start with your reaction.
Yep, balanced equation. you'll notice I wrote down all of the units, that way I'm sure that the units work out.
Right.
And then, what else? Oh, sometimes you have to make assumptions,
Right.
If it doesn't say anything about the temperature, you have to assume a temperature. The best one to assume is standard temperature.
Right, room temperature.
Same thing with pressure. If it doesn't say anything about pressure, you have to assume standard pressure. Okay? So I hope this kind of made sense, and again, it's a little different application of what we've done in class. And good luck.